Okay, so in our last video, it kind of ended right at convergent evolution. So I'm just going to start here again. With convergent evolution, what we see is we see species that do not share a common ancestor converging over the course of time to evolve to look very similar. A lot of times, this is to solve a common problem of living in the same habitat. For example, the streamlined bodies of the dolphin, the ichthyosaur, and the shark, that phenotype, that actual shape, increases speed of the organism. So it's actually selected for. Flight has evolved for different reasons. Maybe it's to find food, to escape predators. But to take flight or take to the air has evolved different times. You could even add into this butterflies or dragonflies, insects with wings as well, would also be convergent evolution. And so when we look at here, you have the evolution of mammals. You have marsupials, which are mammals that, they're not true mammals. The development of the offspring continues in the pouch. Then you have true mammals or placental mammals, and monotremes, which are egg-laying mammals. And so with this, it's kind of cool because over time, there has been an evolution of the animals that live in like North America and Australia, where they look very similar. So here you see the marsupial mouse and a regular mouse, a placental mouse. And so with that, both of them live in similar habitats. And so therefore, by natural selection, they've evolved to look very similar to each other. Rocco. With the flying phalanger and the flying squirrel, same thing, they glide from treetops. So by living in similar habitats, natural selection has favored this extra flap of skin that increases the organism's fitness in that environment. So it's selected for. Now, when we talk about convergent evolution, this kind of can lead to a problem of misleading information in the fossil record. And so, stop. In the fossil record, scientists may see two fossils of a marsupial mouse and a regular placental mouse and assume that they come from a common ancestor when that's not the case. So when you're building phylogenetic trees or cladograms, molecular evidence is stronger as far as the relationships or evolutionary history. Okay, so here's a picture comparing placental mammals and marsupial mammals, and you can see how they've kind of evolved to look very similar because they live in similar habitats, and so therefore similar traits would be considered high fitness. Okay. So here you can see different types of animals throughout the earth that eat ants, and you can kind of see that long snout or that long nose for going into anthills. Now the spiny anteater and the giant anteater, living in different continents, most likely don't have a common ancestor that ate ants. But by eating ants, a longer and longer snout over the years would be considered high fitness, and so they've evolved to look similar. Now, why we're talking about convergent and divergent evolution? Because this falls under the category of homology or homologous structures. So it's really easy to get confused when thinking about like the flipper of a shark or the flipper of a dolphin. They look very similar and you might guess they're homologous structures when in actuality they're analogous structures. And so analogous structures are similar features due to convergent evolution, but not because of common ancestry. The flipper of a penguin, for example, used to be like used for flight in its ancestors. That's different than the front limb of a dolphin that used to be used for walking on land in its ancestor. Now, homologous structures are common ancestry. So you can see here in the front limbs of mammals, the bone structure is similar in all the different species of mammals, but they have different adult forms due to divergent evolution and different natural selection occurring throughout their evolutionary history. Ooh, our next source is the fossil record. And with the fossil record, it's estimated that something like 99% of all life that has ever existed on Earth is already extinct. And one downfall of the fossil record is that not all life leaves a fossil. It's pretty difficult for a worm to leave a fossil. Not impossible, but the conditions would have to be just right for a worm without a skeleton to leave a fossil in Earth's history. And so when we look at the fossil record, what we can, there's my boys. We can see skeletons of dinosaurs and other life on Earth. But what we see is the changes in species, the evolution of species throughout time. We can see in the older rock layers, we can see the rock layers above it, how species have gradually changed. Or they can stay the same, which is called stasis. And then random punctuated change very rapidly would be punctuated equilibrium. We can also see where we have mass extinctions in the fossil record. And one of the cool things is once you have a mass extinction, new species show up afterwards in the fossil record. There's rapid evolution because of all the open niches following a mass extinction. So by looking at the fossil record, we can see that there's been 5 mass extinctions in Earth's history. And we're currently living in the 6th. So when we look at the fossil record in geologic time, life on Earth has existed. Earth itself is about 4.6 billion years old, but life on Earth has been around for about 3.8 billion years. And we can see the gradual changes throughout the fossil record, especially when things with shells and skeletons evolved. Now they're leaving like physical hard evidence behind. So I like this picture kind of showing the simple life. So we have the oldest microfossil pretty far back in time, about 3.5 billion years ago. And then as you move forward in time, you have the first eukaryotes, and then you have plants or things that do like photosynthesis. You have trilobites. This trilobite right here, about 540 million years ago, is a little fossil I sent around in class. And then you have plants. Plants evolve on land about 400 million years ago. And then you kind of can just see the evolution of life on Earth over time. This is another way to look at it, kind of to save space. And so when we look at it, I kind of like this picture, so I've zoomed in here for you. So you have the Cambrian period. You can divide the time period on Earth into different periods and eras and epochs. So you can kind of see, as we go up, ancient life. And then here I'm leaving off with this little triangle-headed organism. Then you go into the time of dinosaurs. Dinosaurs actually lived on Earth for about 180 million years. Or is it 120? They were very successful on Earth. And then you have now all the way up to present day. And we have, okay. So one of my favorite examples of the fossil record that we can see the evolution of species is the evolution of the horse. Yeah. So the horse, about 50 million years ago, its ancestor was a very small forest-dwelling organism. But as continents moved with Pangea and the amount of solar radiation striking the Earth and the climate changed, you had what was once like a forest ecosystem gradually change into like a grassland ecosystem, which then had different selective pressures. So when we look at the evolution of the horse, what used to be the ancestor 50 million years ago was very small. And I know my face is right in the way of the first one about 50 million years ago, but you can kind of see here right above my little face box, you can see like a forest with a small ecosystem. And then as you get into grassland, you can see how the size of the horse was favored and it increased. In class, remind me, and I'll talk more about the legs of the horse. So the ancestor to horses had had 5 digits, 5 toes. And then over time, some of those became like little slivers of bone on the side. So like vestigial structures. And then eventually it got down to like 1 finger. And so now the horse, the hoof where you put the horseshoe is actually its fingernail of its middle finger or its middle toe. And so the horse actually walks on 1 long finger. And what you think of right here as the knee of the horse is actually its ankle bone. And so we can talk more about horses. I think it's its ankle bone, or is it its knee? It's not its knee. Anyway, okay. So let's go ahead though and look at our last piece of evidence, which is biogeography. So in biogeography, it's a study of the geographic distribution of a species. So about 250 million years ago, the Earth's continents, the land masses, were in a supercontinent called Pangea. And over time, the continental drift has shifted our land masses apart. And so we can use that evidence of Pangea, and we can make predictions of where our fossils of species originated. So, for example, when horses evolved, South America and North America were not touching yet. So we would hypothesize that ancestral species of horse would only be found in North America. And so far, the evidence that we have gathered holds that to be true. And so when scientists, kind of interestingly, before they knew about continental drift, they were studying fossil remains in the coast of South America and the coast of Africa. And they couldn't figure out how species, like for example here, skeleton were found in both continents. And they didn't know, how did that happen? Did there used to be a land bridge that connected South America to Africa? How could they possibly explain this? And it wasn't until the 1960s that the hypothesis of continental drift was even proposed. And as we've gathered more evidence, now it's considered a theory that the continents are drifting, and we have plates, etc., things you learn in 6th grade science. And then that explains how fossils from the same time period can be found in the same rock layers, even though the continents have now drifted apart. So biogeography is the study of the geographic distribution of species as evidence for evolution. All right, good job.